live. We are live. And we're live. And hello, the world. We are trying to solve this problem. Well, we just looked at it. It's about a binary tree, so kind of like those types of problems. About trees, about graphs. So that's why I picked it. But otherwise, I don't really know much. So all nodes distance, okay, in binary tree. Given the root of a binary tree, the value of a target node, target, so it's pointer to the target node, okay, and an integer k, return an array of the values of all nodes that have a distance k from the target node. You can return answer in any order, highlighted with bold. So let's look at this example. I have a tree, we have a binary tree, we have target 5, k is 2, and at distance with k, at distance 2 from k, there is 7, 4, and there is 1. Okay, so the nodes that are a distance 2 from the target node have values these. And if there is only one, there is a case where there is only one node, and we're looking for a distance for distance 1. Oh no, it's the target, but the distance is 3, so nothing is at that distance. Number of nodes in the tree is in the range 1 to 500. Okay, the values are from 0 to 500. All the values are unique. So it's a hint. They're all unique. Well, it tells us that I don't know exactly what it tells us. If there was like several ones, by the way, the term value that they use here, in this case, it's a pointer of value of a target node. Because your given target, maybe it's important for nodes that are for trees where, I don't know, that are structured in a different way, and you identify them by the value of the node. I don't know. I'm not sure. But I mean, the idea is it's always a pointer. Node is pointing to another node. Interesting. I mean, okay, so our unique target is the value of one of the nodes in the tree. Okay. So k is up to 8,000. Okay, from could be 0 though. K could be 0. So so binary tree means there is up to there are 2 children at max for each node, and that distance could be in any direction. And that is interesting. So to get all the there is up to 500 nodes. And binary tree could be just one linked list, basically, of just one branch, one long branch of 500 nodes. Could be like that. Or it might have many branches. And I mean, figuring out those downstream nodes that are downstream, k distance, that are a distance 2 downstream. That's kind of intuitive. You go, you do a basically you can do traverse that subtree. You traverse that subtree and see if there are nodes at that distance. So that's one subproblem. Yeah. If we look at this problem and with like two subproblems. One, get all those descendants of this root of the target, descendants at that distance. And we can do that with I guess, with depth first search or breadth first search. Go by levels, and once we get to the level that we need, if we ever get there, then we'll collect all those nodes. If we do depth first search, that means we'll go from 5. Yeah, by the way, from 5, that will include like going to the left, going back. Yeah, so we'll be counting the depth of, and getting, okay, what, 0, that's nil, going back and to the right. Okay, at distance 2, there is 1. And we don't need to go further than this distance. There's nothing there. We're not interested in anything else. So we just need to see if there is that distance value, and we can go back. So, and as we do that, we'll collect them, collect the values. Then, so that's one subproblem. But the other subproblem is the one is the target subtree. The other subproblem is so we were looking at descendants. The other is descendants, right? The other subproblem is ancestors. So let's say there was the ancestors could be, the ones that are above. Okay. And then we could be looking for those in this case, it's siblings, or it could be those uncles, or it could be, I don't know, those those uncles, and well, there is only one sibling in a binary tree, so it's like siblings, but others is basically yes, basically they could be actually lower in the tree, but in a different branch. So are they in a different branch? I mean, they all are in one one branch of a tree. I mean, they all are in one tree. Okay. The main tree. Yeah. So how do we, so ancestors we can get by what? To get the ancestors, we can check from, we go from the root and reach the target. It's quite interesting because we don't know at which level the target is at. So we don't know what ancestor is at that distance. In this case, it's 2, so it's grandparent. Yeah. And there will be how many Yeah, in that tree, there is only one parent in that tree. There is only one parent in that tree. So, yeah, there is only one grandparent. So if it exists, there could be many descendants, but in terms of upstream, if that's the right term, okay, that's another sub-problem. And I mean the brute force solution will be to do breadth first search, count levels, And so find the level of the target and then find the level of, and find that ancestor. So for descendants, it's BFS from target. That will be BFS FS from root to learn level of target. But the other ones, that's what's more interesting. I'm gonna cheat a little bit. Editorial is not available. Okay, but the other ones. Yeah, so no cheating so far. Just one cheating attempt. The other ones are those siblings, those uncles, and so on. Somehow related. So those successors, descendants. Successors, yeah, or descendants, is that the word? So what are descendants? Yeah, I think that's the word, yeah, descendant. From an ancestor, yeah, okay. So descendants, ancestors, and others. Those others, I don't see right now immediately how to identify them. So we will have because we can do what? I mean, we can check their, basically, what is that? What is that one? It's if we go to ancestors of the target and get all other, yeah, because yeah, this ancestor one, which we get its children at 1, because 1 plus 1 is 2. If there was an ancestor 2, yeah, if the length, if the distance was like 3, then we will check the children of this ancestor. Yeah, the parent will check the stepchildren, the grandchildren of the parents. So 1, 2, 1, 2, 3. So, but we don't want to go and get the grandchildren of these of the 3 here. So other than the target. And this way we check all the ancestors till k distance. Yeah, so we'll start with k distance. Basically, the closer we get to the target, yeah, so get the children, but we don't go By the way, yeah, we don't go, like, if there is a child, if we were looking at this at K3 and there was more children here, so 1 would be, okay, like 1, 2, so 3 would be fine. But yeah, if the K was 4, so 1, 2, 3, 4, so that will not be a distance 4, that will be a distance 2. So this grandchildren of this ancestor should not be included also, which means which kind of means, because we are looking at the shortest path, and yeah, if k was 3, then we'll get these two. These will be excluded. So 1, 2, 3, 2, 3. So that suggests, yeah, we're still working on this others case. How to how to not get the wrong ones. That's the thing. When we will be checking the ancestors, the furthest ancestor is the one at the k distance is the target. Not the target, is part of the answer. Now the other ones, they need our special attention. So if it's 2, this one will go. I think I need to draw. Yeah, I need to draw. Okay. Pen and paper, because yeah, it really helps to draw, and I think that's one of the cases which really where it's important. So we'll have let's look at this. Let me look at this. We'll have we have this. Let's see, we have this 3, we have this 5, we have this 1. Where's my pencil? And we have 6, and we have 2, and we have 0 and 8. And it's all good. Yeah, 5 is the target. Five is the target. Now, so if k is, and I want to explore the ancestors. So let's say there is an ancestor at I don't know, this value 9. see, there's another ancestor here, and it has the axis is here, 1, 2, 3, 4, 1, 2, 3. Let's say it has another child, that ancestor, and let's say it's 4 here. So, and let's say the k is 2, right? K is 2 or k is 3. Yeah, if k is 2, then we'll have this 9. Yeah. But I want to see more. I want to see k3. Yeah, let's do k3. So that will k3. How do we do that? Yeah, I want to try that. K3 will mean, so that will mean, yeah, with its descendants is all clear. It's kind of clear, but the ancestors, yeah. So we know the level of 5. We can start from the root of the tree. We know it's the level of target. We know it's like level 1, 2. Yeah, if we start with 0. So it's level 2. We know we have 3, so that means when we start with 0, the difference is 2. And we have 1 more to go. Okay? But it cannot be that 3. How do we know that? That's the question. 27 minutes finding the logic. I think I should have. Yeah, it looks like I'm a little bit out of rusty. I'm a little rusty about binary trees. Yeah. Because usually, I mean, for an interview, you want to be pretty much finishing code by that time, by 30 minutes. Yeah, just refining it with the last 10 minutes if needed, like debugging or something like that, just doing test cases. But in this case, yeah, it's 30 minutes is coming. I think I'm kind of close to, but the key sub problems close to the solution. The key sub problem right now is, how do we know if we look at this ancestor, how do we know that we can't count that remainder length that we need, remainder distance, remaining distance? So in this case, it's just 1. Yeah, it will be 1 to the side, but in the direction of 5, we don't go in the direction of the target, because it gets closer, and it's a different sub root. It's a different sub tree. So at that specific root, we only want to go in the direction opposite from the target. That's, yeah. So we want to avoid the subtree that the subtree where the target is. So if it's in the left subtree, yeah, we don't go there. In this case, it's in the left subtree. Yeah, okay. So first thing, well, we know the levels, and so no subtree L or R, and go remaining distance in the opposite subtree. Yeah. Go remaining distance in the opposite subtree. Yeah, that's kind of the, and that pretty much includes the ancestor. Yeah, so we will be go for each ancestor within K. We'll be doing that basically. Yeah. For each ancestor within K, right? So there will be, yeah, that ancestor. But we will get all of the nodes at that distance from that specific ancestor, excluding, but we will not, yeah, we will just, basically we know it's like, for in this case, we avoid left, and we will give it a subtree that where we need to go. Like in this case, we will not go from this 3, we will not go to 5 side. We'll exclude that. We'll just we'll give that subtree with root 1, and we'll know that minus 2, so with distance 0 that we need to go. In this case, it's 0, but it will be different in other cases. And by the way, 5 is also, and from 5 we need to go 2. Okay, so from 3, but from 5 we need to check all of the, yeah, it's a kind of a special case. It looks like we need to check all of its children, but with ancestors we check only the children in the opposite subtree. Yeah, only the children in the opposite subtree. Yeah, that sounds right. So 33 minutes, and I think we found the logic, but it looks like it's 2 cases here. Yeah, this descendants and the ancestors. Yeah. So we need to know the levels, and from root on the level of target, and then go remain in distance from opposite subtree. It looks like a fast traversal for all of these, but I'm also thinking about like a more universal solution, a solution that will fit, that will take care of all the cases here. I mean, but it's a directional graph. The tree, you can't go up, so I can't. I mean, if it was a if I could go up from that, if I could go in any direction, I would just do breadth first search from target. At k levels. Pretty simple, yeah. It's pretty simple. Yeah, you just go layer by layer, or this row by row, and collect all those at that distance. But with a tree, you can't go back, right? I mean, you kind of do, but can you do a breadth first search that involves going back, just like going upstream, just like going down? If we can do that, that will be a universal solution. Yeah. If we I mean, but finding the target, you can't go from the target up. You can, if we go from the main route and if we go from the main route, and then at some point we find that target, then, I mean, we can obviously traverse from the target, but what if it's something like very simple and even stupid solution? If we do depth first search, would that help? Would that help? Would that help? Depth first search. Yeah, because we can do depth and just check all of them at that distance from the target. And then we'll go back and we'll go back. And let's say we go back and continue counting. Once we hit the target, we start counting those that are downstream. Okay. Once we're done with that node, doing depth first search, we'll go to the previous node and we continue counting that distance. If we continue doing that, so let's say we pass, if it's target, yeah, And yeah, if we could continue doing that, then it will also give us a solution. Okay, yeah, okay, we go into several directions, but if the node is, if node is a target, then it should return something special, and it should call the next ones with something special, some value which is actually the distance, which will be tracking distance. It should also return that distance. It looks like, okay, it looks like this. If root, so if root we're looking for is target, okay, then then let's say that it that this parameter, the next calls it does, and the return values. Okay, so I'm not sure we can do that all in one function, do that one main function recursive, but I feel like we could do that in a helper function. So that there will be a function DFS, and it will be func that will be getting the node, and it will be returning, and we'll be getting also, should it be getting anything as a parameter? Because here is the deal. We want to increase that. If yeah, it should be returning an integer, and it should be getting an integer as well. Also, this distance and node, tree node, and but the trick is here. Okay, so I mean, obviously, if root is nil, return 0. Okay, but if root is target, we actually want to, first of all, there it will be yeah, the difference will be, yeah, we'll create this distance if root is target, then we actually change the distance. So distance becomes 1. Okay. Now, if we got to some node and distance was not 0, because initially we called DFS with root and 0, but at some point let's call it dist. If dist is not so bigger than 0, and we have the distance right now. So that means we need to increase distance and when we get to, we need to increase the distance. But I mean, in the previous calls, in the ancestor calls, the distance was 0. Okay? But we will return, if the returned distance, we will also return something. That will be called, this DFS will be called for node left. DFS will be called for node right. And for dist. So we'll go Do we need to increase distance like that? I mean, if we're just going over, the distance is always 0 until we actually get to our target. So that's what I'm trying to do. Distance will change once we are at the target. If we are not, oh, by the way, if it's target or distance is not 0, or distance is not 0, or basically, bigger, then increase it by 1. Okay, now these calls will return us something. And for example, and we need to return something. And we will return distance. Once we do our calls, but I mean, so 5, we added the distance. If distance equals k, then we append a result is a slice of integers. Then if distance is k, we append answer is append answer and node val, right? So the downstream, what will happen with the downstream? Okay, we'll call them, and in each next call, the distance will be from 5 will be added, but and in each next call it will be additional distance, but only when the distance is k we will append them, and it's quite clear. But what if we are at some ancestor level and so 3 will receive something from 5. And we wanted to receive 1. So 3 is not a root. 3 sees that and by the way, we want to 3 will get some 3 will do the calls. So it's not nil, it's not the root. The distance is still 0, but the distance should not be 0. That's the thing. That is the thing. So distance, we should check if distance is 0 after. Yeah, so we'll get from the left, dist will be that. So if that subtree returns, so if that not 0, so that means we had some distance, and that means we need to add dist also. If that's not 0, or basically, yeah, more than 0, we're also adding distance. So it looks like this should happen after. Or how res, right? So so it looks like if root is nil, okay. If root is target, okay, we have the first. And by the way, do we count the distance? Yeah, we have 1, but the distance at 3 will be 1 actually. So the distance if we have the root and we change the distance, because the distance is the number of edges, it's not the number of nodes in the chain. So it's gonna be too long in this case. Yeah. I mean, we can initialize it as -1. And if we hit the target, it becomes 0. And or if we somewhere downstream, if we are downstream, we also but look at that. So 2 will be like, okay, I see, I get the distance that's already if distance is k append distance. We can do it here so that we don't change it before. Yeah, and that way we can still start with 0. So, but then so let's check the downstream. We have a target, and now distance becomes 1. Okay. And we could do the call for 6. 6 sees positive distance, and okay, it's not nil. Distance is not k. The distance is positive. So 6 goes, okay, distance plus 1. Okay. And we call with that distance of 2 the next nodes, but they're nil. So it basically just returns zeros and zeros, and 6 gets just 2 zeros, and that's it. It doesn't, and it returns. So 6 returns, by the way, 2. Because so 6 gets 2 zeros, and the distance at 6 was 2. So it will return 2 to 5. 5, what 5 did, it identified as a target, and it got the values. It already identified as a target. It did not append itself because it was not at the right distance. It was. So it's basically just checking if it's above. Yeah, it adds. So 5 adds and increments distance again, which it shouldn't be doing. 5 should return distance 1. Okay, but in this case it will in this case wait a second. In this case it was 5 saw so 5 was a target. It increased the incremented distance by 1. It will also increment distance by 1 and by 1. Which means we don't want to do. That's already a problem here. But I mean, if we go downstream again, so 5 will call, well, 5 will call its, oh wait a second, from the left child, it got, it increase, but okay, what we'll get from the right child? Okay, it calls 2. Yeah, 2 will already have a like distance of 2. So 2 will get appended. Yeah, we don't want to do that. We don't want to do that. We don't want to append it every time, because that will be more than 0. Yeah, and I think we're kind of in the direction, but we need to play a little bit more with it. It's 1 hour. Yeah, we've been working on it for 1 hour. It's probably a good time to take a break. And yeah, take a break and see if we can do like finish this thing in the second round. So thank you for watching. That was our live random LeetCode. Not so random, but good attempt, I think. And we'll see you in the next video.